This movie is going to be about how we can use the Team software to rebuild maps that were previously collected in Team. One of the reasons why you might want to rebuild a map is because it might be that in the original collected map you might not have had the element list quite right. Or it might be that you want to modify the phase list, build your own phases, which can be done as part of the review process, the rebuilding process. Or there is the possibility that you want to do a net intensity map, or you want to remove overlaps that were present in a map. The map that you see on the screen now is a map that was collected, and it does have an overlap. It has an overlap between phosphorus K and zirconium L. And so let me just show you, if we click on element to phase, we can actually show a number of maps here. So for instance, one of the things we can always do is we can do a show all that puts all of the maps on the screen, including an overlay. If we scroll on down, you can display 9 of the maps here, where some of the maps, for instance, you might notice the phosphorus K and the zirconium L map look almost the same. Although if you look at it carefully, you'll see that the brightest part of the phosphorus map is a little bit different from the not quite so bright. Whereas what was not quite so bright in the phosphorus map is a little bit brighter in the zirconium map. And you would further see, if you look at it carefully, that the brightest part of the zirconium map overlaps pretty well with a phase that's in the silicon map. And the phase in this case is actually zirconium silicate. The mineral is zircon. It's ZrSiO4 is the formula. Now, in the case of the phosphorus, what is associated with the high intensity in the phosphorus map is actually the calcium. And the mineral there is apatite, and it's a calcium phosphate. And so that is what is really happening. But if you look at only the phosphorus and the zirconium, you'll see that in our ROI maps, ROI means region of interest, we don't really take care of that overlap terribly well. And so this would be a reason why we might want to rebuild our phase maps, or rebuild our previously collected map. Now, when we double click on any of the maps from the project panel, you'll come into review data mode, and then there will be a button in the far right called rebuild maps. If we come back to the map type, there are 3 possibilities here. One is phase map, one is net intensity, and one is ZAF. In this movie, we're going to show you the phase map, we're going to show you the net intensity map, and we'll just describe what happens in the ZAF map. Basically, in the phase map, what's going to happen is we're going to rebuild the map. And you might wonder, well, again, why would you rebuild a phase map? You already have a phase map. Well, it might be that your element list is not correct. You want to clean it up a little bit, make the element list a little bit better, or make it perfect. There is also the possibility that even if you leave the element list exactly the same, that your phase map could behave, you could see a slightly different phase map. And the reason why that is that when we rebuild the phase map, we are not doing the same procedure exactly that we did while collecting the map originally. In the rebuilding of the phase map, we start having all the spectral information. And then all we do is, when successive examinations of the data, or successive frames, you might think that it's frames, in reality it's successive re-examinations of the data, we actually are doing a refined examination and trying to see if we can get a little more sensitive. And quite often we can. So we'll show you the phase map first. So I click on phase map and I click on rebuild. Now it's going to take a little while for it to rebuild the map. And I think we'll see. It takes probably certainly a little over a minute to do this normally, but since I'm recording the movie, it probably is going to get a little bit slower yet. Now, what I'm going to do here is I'm actually going to change. I have carbon on my list, but for the most part, the carbon is from a coating in the sample. It's not really going to be of very much diagnostic value. Manganese was a trace, almost a trace, in one of the iron-rich phases, and I think I can probably get rid of that one. Now, something you should be aware of anytime you see the possible elements dialog box is there is, at the far right here, something called ZAF list selection. And if you click on that, you'll see that we have a way to examine our elements for quantitative analysis. In this case, we're not as concerned about quantitative analysis as we are with mapping. So for mapping purposes, the choices that I have would be, for instance, something like iron K. For instance, you'll see there is a possibility I could select iron L rather than iron K. And in fact, for mapping, I could actually map both iron K and iron L. Now, I don't like to do that only because I think it confuses the phase map a little bit, because then the phase will be called iron K, iron L, and oxygen and silicon. And I think it just is confusing to have two irons in there. So we'll leave that one alone. For the zirconium, though, there is a possibility we could do zirconium L or zirconium M. But zirconium M is at extremely low energy, and it overlaps too many things. We're not going to bother with that. We're going to leave that at zirconium L. So now let's just go ahead, we click OK, and this is when the map really starts to build seriously. This is where I'll probably start to pause the movie recording, just to let it almost finish, and then we'll resume recording of the movie. And so I click OK. In the upper right, you'll see it says rebuilding maps, and then it says rebuilding, ... You may have seen the number 1 flash on the screen. And then what's happening now is you see that the image starts to come down, and it comes down pretty slowly. And it's probably not, I think it's going to be a little over a minute on most systems. It'll be a little slower here if I let it go. So I'm going to pause the recording, which would make it speed up a little bit. Okay, now it's almost done with this first pass where it's just loading in the data. And now it's going to fairly quickly go through a series of passes here, trying to clean up the data a little bit. Sometimes you'll see the little green line sweeping the screen, and sometimes you won't while we're recording it. On a live system or on a real system without the movie and so forth, I think you actually would see it. And so we are pretty much done, though. And so now it just says it's rebuilding, and it should be done pretty. Now it says it's saving the data. So not only is it going to save the data, but eventually then it's going to take the phase information that we have here and generate spectra, as it says here in the upper right. By generating spectra, it means it's going to collect the phase spectra. We have, well, quite a few phases here. I can show you the phases when we're done here. So we'll let it generate those. We've been in a mode that's referred to as the element to phase rather than phase to element. Okay. So if I were to change that back to phase to element, and then double click on this map to reopen it, what you'll see are the phases here. And so, for instance, there's 1, 2, probably 3, 4, 5, 6, 7, 8, 9, 10 phases here. So that's what it got for the phase analysis. The colors are different. I wouldn't necessarily say this one is significantly different from the original in terms of the phase information provided here, though. If I were to just click on a phase, like for instance, there is a green phase here. Let me see if I can. Yeah, there's a silicon iron phase. Then there's a red phase. And so there's a variety of phases. Also showing us the phase spectrum here, which I don't really need to see. So let's go ahead and so there are a variety of phases that were determined, and that's fine. Now what we want to do is to look at the individual maps. Now as it turns out, to do that, I'll click on Element to Phase. And just like before, if I want to, I can click on Show All. And it'll show me these. And it shows me again the phosphorus zirconium. These maps should not be any different at all from the original maps, aside from the fact that I've removed a couple of elements. I removed manganese K and I removed carbon K out of this. And of course, it's possible I could have added additional elements, or I could have done copper L instead of copper K, or if those elements were present here. All right, so now what we're going to do is I'm going to rebuild the map again. But in this case, what we will do is I'm going to choose net intensity. Now, what we get when we rebuild the maps for net intensity is you might assume that all we're going to do is remove background, making net counts. And actually, yeah, we kind of do remove the background, except that in almost all maps that I've ever collected, or that almost any of you will ever collect, there really isn't any background. In fact, if you look at how many background counts there are in each channel in a spectrum, it's probably somewhere between 0 and 1 counts per second. And as a matter of fact, it's a lot closer to 0 than it is to 1. So effectively, there really isn't much background in most maps. Unless you collected a map over the weekend, maybe you might get better quality data there, and that might actually happen, that you'll actually get background. So yeah, in a sense, we do remove background, but for the most part, we don't. In fact, there's a number here called threshold, and right now it's set to 80. And that threshold is referring to how high a peak is in counts, or how high the highest peak is. Sorry, let me say that right. How high the highest peak is in a spectrum at a pixel before we will do a background. So if it doesn't have at least 80 counts at the highest channel in our spectrum, it's not going to bother even trying to do the background. It's going to assume the background is 0. And so if we make this number something quite high, like say 200 would be relatively high, then what would happen is we'll probably never calculate a background, and we'll assume it's 0 everywhere. If we make this number very low, like perhaps something like 30 or 40, perhaps maybe 50, something like that, what will happen is that the background will be fit for almost every single spectrum that we have, and the result is that we will end up with background misfitting artifacts that will probably steal away legitimate counts from some of our maps. So my guess is, and my recommendation would be, that probably leaving this set at a value, or a threshold value of 80 to 100 is probably going to be good for most spectra, most maps when we rebuild them as net intensity maps. Now also, though, we said the net intensity is going to try to remove the background, although there probably really isn't any background. So then what does a net intensity map do that's significant? And what it does do is it also does a pretty good job of removing deconvolutions. So in the case of this map where we have phosphorus and zirconium overlapping, we're going to expect that the net intensity map will make a difference. So now I'm going to rebuild the map again. Now there's not a lot to see while this is mapping. All you're going to see is, if you're patient and watch, it's going to take probably, again, something like a minute or two, and probably if I recorded the whole thing, it would be 2 or 3 minutes. And if I actually turn off the recording, we would probably find that it'll finish a lot faster. So let me pause the recording, and I'll resume the recording when it's done or almost done. All right, it's done rebuilding the net intensity maps. I had intended to actually pause it just as it was almost done, but it turns out it is done now. Now, there's actually 2 tabs over here, one called ROI map, one called NetMap 1. Now, right now we're on the NetMap 1, and if you look at the maps that we're seeing here, you can see that the zirconium and the phosphorus maps are quite different. There's a mislabeling problem here, that the zirconium L is really labeled as zirconium K, but there's no way that's zirconium L. And the reason why is, where this map was collected at 20 kV, we would never have enough data to see anything in the zirconium K, and we wouldn't have the overlap with the zirconium and the phosphorus. And so if I then just click on ROI map, the tab in the upper right part here, eventually it'll just transfer back so that we can actually see displayed in the screen the phosphorus and the zirconium. And if we, again, now click on NetMap, watch those 2 maps. As soon as I click, we'll see them change. And so you can see in both of these maps that in the net maps, we are pretty well getting rid of the overlap that was there before. Now, there is always the possibility that we could modify these list of maps that we've got here to get rid of the ones we don't really care about. For instance, if you hover over our map, you'll get an X. You can click on that X. It gets rid of it. I'm going to leave the calcium map. I'm going to leave the silicon. I'm going to get rid of pretty much all of them. So I only have 4 maps left. And aluminum, you'll get rid of that one. Okay, so now we see these 4 maps. And I can also hide what I have here on the right. I'm going to try to hide what's on the right. Okay, so now we see the 4 maps. And as you look at it, in the phosphorus map, you actually can see kind of a ghost of speckly noise from where the zirconium overlap used to be. There's still a little bit of it there, but we've gotten rid of the overwhelming majority of it. And if you look at the zirconium map, you'll see that we've gotten rid of almost all of that overlap. There's a little bit of speckles and noise and so forth. Now, the reason why I've left the silicon map up here is you can see that the silicon map and the zirconium map, there is some similarities. Wherever we have these bright areas in zirconium, there actually is some silicon there. It's not the brightest part of the silicon map, because the brightest part is actually silicon oxide here. But in terms of zirconium silicate, we do see a very good association and correlation of what we see in the zirconium map. We can find a representation of that same phase in the silicon map. And similarly, when we look at the phosphorus map, you can see that wherever the phosphorus is high, basically the calcium is always high. I think there are some other calcium-containing phases in here, but that's not very high calcium. And the highest calcium phase in here is the calcium phosphate. And again, a very good correlation between these two maps. And so, and then when I want to, I can always show everything back again. And I could, let me get rid of those. Okay, if I go back to ROI maps, again, it's going to show me all of them. But again, I just want to highlight the fact that we've got the overlap between phosphorus and zirconium is present in both the phosphorus and the zirconium map. Okay, that concludes the introduction to this. As I said, there is another map type that you could do, and I mentioned this briefly. One of the map types says ZAF. If you click on the map when it says ZAF, you will not only get a net intensity map, you'll also get a ZAF weight percent map, ZAF corrected weight percent map, and a ZAF corrected atomic percent map. Now, at first thought, you might think, well, why don't I just go ahead and do that? And it turns out the net intensity map you can get all on its own, or you can get it as one of the ZAF maps. And the reason why we do that is the net intensity in the deconvolution is really the first step in doing a ZAF analysis. But one of the things before you start thinking that you're going to get a lot more information out of the weight percent and the atomic percent, you're not really, because if you really ever look at what is the spectrum quality of a single pixel, you'll see that there are very few counts in it. In fact, you'd wonder why would we ever get any good information from it. It's amazing how good those maps look, the ZAF weight and the ZAF atomic percent, when you realize how little data is really present in a pixel. Now, also what happens is that you'll see that the ZAF weight percent map and the ZAF atomic percent map will look very similar to the net intensity map. Maps, images are, by their nature, somewhat qualitative, not really so much quantitative. And so you'll see you'll get almost all the information, the good information you want, you can get from the net intensity maps. You almost don't really need to do the weight percent or the atomic percent maps. And the deconvolution really is the most significant effect. And so we get that out of the net intensity maps. Now also doing the ZAF maps will take significantly longer, probably 2.5 times longer than it will take to do the net intensity maps all by themselves. All right, so that concludes our presentation on how we can rebuild maps in the TEAM software. Thank you.